Okay, as you all know, this is the last lecture of the class. Next Monday, we are going to have uh, a an exam. I forgot the exam. We are going to have an exam. And Wednesday is a wellness day, so we are not going to have any class. As if you recall, we talked about having one online class. Essentially, I will record a review of the final exam, then post it on Blackboard, just to cover for the lecture I had to cancel because of that whole vaccination thing. So, and then the next one, the next lecture, the last one, April 26th, we will have graduate presentations. Okay, there are a couple of graduate students in class. So those of you who have registered, those graduate students who have registered for a face-to-face lecture, they have to come to the board and present their projects. And if you are an online student, you have to send me your presentation, a recorded version of your presentation with your teammates. And yeah, and I will send you a couple of questions. I mean, I will talk to the online students. I will send an email to the online students so we can discuss it a little further with them. Is there any questions about the course schedule, the classes, the lectures, or the exam? We talked about the exam. You'll probably get 5 conceptual questions and 3 problems for graduate students, 2 problems for undergrads, right? That was the agreement we had, right? And you will have 75 minutes. I'm trying to make sure that you won't need more than 75 minutes. If you needed more time, we will, of course, extend the time. If I see like more than half the class needs more time, but my goal is not to stay between the time frame allocated for the class. Stay within that time frame. Is there any questions? Okay, that's good. I just recently updated your attendance grade, which was a surprise to a couple of people for some reason. If you didn't turn in your attendance quiz, you won't get an attendance grade, right? That was the deal from the beginning, right? But I received a couple of emails from some people, just 1 or 2 emails, that were very surprised about their attendance grade. And I guess they didn't watch any of the lectures because they didn't know about the deal we had. They didn't go through the syllabus. Yeah, I'm pretty sure most of you have seen your updated attendance graph. If you have turned in your attendance quiz, you have been credited for it. If you were in class, we actually have a case that a student was in class, forgot to turn in their attendance grade. I actually went in and updated the grade as well. So this is based on trust. If you tell me you have been in the class, I trust you. But if you haven't watched the lectures, especially if you're an online student, if you haven't turned in your attendance quiz, you can't have any claims here, right? I guess that makes sense. That makes a lot of sense, at least to me. Yeah, so your attendance grades are updated, and we also said that I think from a couple of weeks ago we had attendance quiz for every lecture, and I also said that in the beginning of the lecture. So if you were in class or if you watched that lecture, you would have known about this beforehand. Okay. Is there any questions about your attendance grades? No? We actually had more attendance quizzes than what is posted on Blackboard, but I decided to give everyone a present mark on the rest of the, like we had a couple in February, we had a couple in March, like 1 or 2 in March, but I didn't include any of those. Yeah, I guess that's it for the attendance grade. Attendance grade is if you have gone over the syllabus or if you came in for the first lecture. Attendance grade is 10%, I think 10% for the undergrads and 5% for the graduate students in class. The idea was from the get-go that you don't need to be present in class, but you have to watch the lectures, right? And you will be checked randomly through attendance quizzes. That was the agreement from the beginning of the class. So if you send me an email and act surprised that you didn't know this, or if you like why my attendance grade got hit because I just updated it, and you weren't attending the class and you didn't have any excuse for not attending the class or not watching the lecture, your attendance grade will take a hit, of course. Okay, so if there is no question about that, about any grades in general, we can move on to the exam 2 review. Is there any questions? No? Okay. So let's move on to the exam 2 review. The handouts I've given to you are essentially a compilation of some questions that will probably show up on the exam, and these will complement your homework, essentially. The first 17 questions are what I've done was I went through your lecture notes, my lecture notes that I have given to you, and I extracted whatever conceptual question I can give to you. So there is no question there's no question other than this. There's no conceptual questions in the lecture notes other than these, right? And yeah, so what we're going to do today, we will go over them one by one, especially the conceptual ones, and then we'll solve the problem number 17. We will go to some homework problems. We will talk about those, and that will be it. Yeah. And whoever can answer, yes. So you said for this exam we're allowed to bring a sheet of paper with some notes or formulas on it? Can you repeat the question? For the next exam, you said we're allowed to bring a sheet of paper front and back. Okay, yeah. So the question is, whether you can, what you can bring to the exam. Just a two-sided sheet of equation sheet, cheat sheet, right? Two-sided letter-sized equation sheet. So exam is not an open book, an open notes exam. This is the only thing you are allowed to bring. I guess it is a little harder for me to check on the online students, but there's no other way. I mean, the only thing I could ask them it was to be present during the exam time. There are a couple of people who can't make it to the exam, and I am going to have individual arrangements with them. But other than that, if you haven't already talked to me about not being able to attend the exam, you have to be present in class if you have registered for the face-to-face instructions, which includes all of the undergraduate students, and you have to be present virtually if you have registered for the online part of the class. Any other questions? Okay.
Sorry, this is for exam 2 or final?
Both of them. Yeah. So we are not going to have any open book exams anymore, because open book exams are going to be harder. So we don't want to have harder exams. So let's go over the questions one by one. And whoever can answer these questions will get a bonus point. I have a pen. I will write your name. You will get a bonus point, right? And yes, if you are an online student and if you answer these questions, the first person who answers these questions will get a bonus point. Let me put this one. The first one we have here is, what is the design target in aerospace design?
CD by L should decrease.
CD by L should decrease.
CD by L.
You were okay. You were getting close, but it wasn't the correct solution. Lift to drag ratio. Lift to drag ratio should be maximized, right? Okay, that's the design target. We cannot compare the drag coefficient with a lift force, right? If you're comparing the coefficient, it has to be, both of them have to be coefficients, and they have to be maximized. Max got it right, who is present online. So I'm going to write his name for a bonus point. Next one. This is the question you probably will get on an exam. This is the type of question. Draw a typical CL versus alpha figure, which I'm going to draw right now. CL versus alpha. Okay, that's the first part of it. Show where zero lift angle of attack is. Where is that? Where is the zero lift angle of attack? Where is it on this figure?
It's negative.
Where, what point? Zero lift angle of attack can be negative, positive, or zero. Doesn't have to be negative. Yes. Thank you. Right, depending on your airfoil, it can be right from here or here. This, where your line crosses the x-axis, is the zero lift angle of attack. Okay, this doesn't have to be negative. It can be 0 for a symmetrical airfoil. And for negative camber, it can actually become positive, which is a very unpopular, uncommon case. Okay, so what was it? I keep, okay, for latent, right? And where the stall angle of attack is? The maximum point, yeah, right here. So your stall angle of attack is going to be right here. Muhammad. I didn't expect this much engagement. It's good. Keep it up. And where does the flow separation happen?
After the stall condition, we have decrease in CL and again increasing and then decreasing because of flow separation.
Okay. So here is where the flow separation happens, right? Right? Okay. A lot of bonus points going around. Fatima. And why does the CL increase after the initial stall drop?
Because as the angle goes up, the flow stops separating for some period of time.
What happens?
Uh,
What do we call that phenomena? So what happens is when you have flow separation on a wing, right? You have a region in which the flow is rotating around itself, right?
Right.
And then this goes away, right? This departs the surface. That's what you were saying, right? This phenomena is called the vortex shedding. Which is more closely studied in like a von Karman tunnel, but that's beyond the point. So, Matthew, right? No, I know a lot of you. And what's the next one? What can you say about the slope of the line before the stall condition? That how does it change? That's okay. What does it mean? It is 2 pi for a thin airfoil, right? It means that it changes linearly. That's the thing, not the value. Right? I'm going to give the bonus to both of you. Linearly, it will change linearly. For a thin airfoil, that is 2 pi. That's the slope. If it's linear change means that the slope is going to be only one number. Okay, Jacob and Trevor. Okay, so that's the second question. This is, I would say, the most extensive question you can get as far as the conceptual questions goes. You probably need to explain the vortex shedding phenomena if you were to get this question on the exam. So you have to learn it a little better. You have these on the lecture notes. You can always go back to them and learn it better. And also on an equation sheet, you can only include equations. Okay? So I want to make sure you learn these concepts. You cannot include the content because I'm giving you all of the conceptual questions you can get. You cannot just put the answer on the equation sheet and bring it to class. Okay? Does this make sense? But I want to test how much you have learned them, right? One may argue that exams are not the best way to test your knowledge. I agree, but we don't want to change the system in one course, right? So question number 3, what would be the difference between a symmetrical airfoil and a cambered airfoil in lift generation? Yes, let's go with someone new first. Let's see if there's Paul.
So a symmetrical airflow creates zero lift at zero angle of attack.
Exactly. So the main thing that happens with a symmetrical airfoil is that at zero angle of attack, you won't be able to generate any lift. Let's say this is your symmetrical airfoil. If your angle of attack is 0, then lift is going to be 0, which is not the case for a cambered airfoil. Paul. Okay. Fourth question. Why is the drag coefficient, and there's a grammatical error here. Why is the drag coefficient sensitive to the Reynolds number? This one is the toughest one. Yes. Why CD changes with alpha? Changes with Reynolds number, sorry, not that. Why? Let's see if there's someone new who can answer that. Okay. Yeah. Anyone? We have a couple of people who have not had any answers yet. Just think about it. What would changes in Reynolds number signify? How does it relate to drag?
Change in viscous forces
Okay. Which
would relate to drag.
how so exactly. So that the main answer here is that when you are having your Reynolds number, change in Reynolds number, go back to the analysis on the viscous drag coefficient we had, right? If you increase the Reynolds number, what's going to happen? You're essentially increasing the velocity, right, V infinity. Your body layer regime is going to be affected, right? Which means that your viscous drag is also going to be affected. For a higher velocity, your pressure distribution also is going to be affected, which your pressure drag, which is going to change your pressure drag. Also, the flow separation, all of those things are going to be affected, which directly contribute to your drag coefficient, which is not necessarily the case when it comes to other parameters here. What was your name? Wyatt, yeah. Okay. Yes. That was the idea. That the body layer thickness was directly related. Not, I mean, inversely related, but it was related to, based on the equations we had, right? You remember the equation for turbulent body layer, all of those things, right? And Reynolds number is a function of your velocity, also the length from the flat plate. So a change in Reynolds number is going to change your body layer thickness. That's for sure. That was the equation. Delta is equals to, what was it 0.5, 0.05 divided by RE of x. You remember that? 5, say yeah, I just remember the equation. For a laminar flow, it's 5.0 x by RE of x, right? And we also had a friction coefficient equation that was related to Reynolds number. Okay. So let's move on to the fifth question. What is the aerodynamic center? What are the differences between aerodynamic center and center of pressure? Exactly. So aerodynamic center is the point where moment is independent of angle of attack. So what about the rest? What is the difference between? Zero. So aerodynamics, exactly. Aerodynamic center, moment doesn't change with the angle of attack. Center of pressure is where the moment is going to be zero. Drew, right? Ryan? Who's Drew? Drew, yeah. Sorry. I got you. Yeah. Okay, next one. What is the Koda condition?
Isn't that essentially says that the flow pattern will be sharply trailing edge like smoothly?
Can you repeat what you said?
That the flow pattern will be like a sharp trailing edge smoothly.
That's right. The flow will leave the trailing edge very smoothly, right? If you have this type of trailing edge, you can conclude that the velocity for the flow to leave your trailing edge smoothly, these velocities have to be zero, right? The upper surface and lower surface velocity. If you have a cusp at the end, at the trailing edge, since they are in the same direction, your V2 has to be equal to V1, has to be equal to a constant. John. Okay. How is the Koda condition satisfied in real world? This is actually something we discussed in class as well, very briefly, but it is on your lecture notes. viscosity is the link here. The color condition satisfies through the existence of viscosity, right? Okay. Next question. What is the Kelvin circulation theorem? Did you answered one question? Let everyone else answer. Yes. No. The leading edge starts to separate. No. Right. I mean, can you elaborate? I'm not sure what you mean.
I just remember like on the picture of the airfoil, like the arrows were starting to on the trailing edge, sorry, at the edge, towards the end of the airfoil, and then
Wasn't that the trailing edge stall, or?
I think it was because it was like talking about like the end, and then for the leading edge, it was starting to stall more in the middle, and then
Yeah. That's the different stall patterns, right? Kelvin circulation theorem. Someone new. Just wait to see. I want everyone to get a bonus point. And then you have the questions in front of you. You can just go and find the answer to the future questions. Get bonuses. Anyone? No. Okay, so let's go back to.
the circulation continues after the end of the airfoil.
The idea with the circulation is conserved, right? Yeah. That was the main idea. So D, let me write it here. Total derivative of circulation is 0. Circulation is conserved. Okay, and Leighton. Okay, so next one, explain the leading edge, trailing edge, and the thin airfoil stall. What is the difference between them? Do you want to?
Towards the trailing edge, it starts to
Flow starts to separate, right?
at the back. At the leading edge, it works its way up and it starts to separate sooner, and then at the I think it's like the
Flat plate, yeah.
flat edge, it separates at like the very beginning.
Exactly. So for a trailing edge start, your stall starts at the trailing edge. The flow separation starts here. Flow starts to separate here. For a leading edge start, it suddenly separates from the leading edge, or it will move its way up very quickly compared to the trailing edge stall. And flat plate, because of the edges, your stall actually happens. It is essentially the same condition as a leading edge stall, but your stall happens much earlier in the flat plate. I'm sorry, thin airfoils, very thin airfoils, or which are essentially flat plates. And I mean, we just talked about the differences between them. What is the difference between these three stall conditions when it comes to the lift coefficient at the stall? Which one has a higher lift coefficient? Which one has a lower lift coefficient? Let's see if there is anyone. I don't know who hasn't participated. Okay. Let's go, Mohammed. We don't have any volunteers. Trailing edge, right? It's a little damper, right? So you're getting in your CL versus alpha figure, like here, based on what Mohammed is telling us, Your leading edge stall is going to look like this. Trailing edge stall is going to look like this, right? Flat plate will be like this, right? Okay. So let's move on to the next question. How do we calculate the stall velocity during cruise condition? What is the equation? You answer, right? Let's give it like 30 seconds for others. So this is how it's going to go. I'm going to ask the question. If you haven't participated, you will get 30 seconds to participate. If you don't want to participate, it will go to the first person who will have his or her hands up. Okay? Because the 30 seconds has already passed, so let's go with John.
Isn't it the square root of 2W over rho SCL max?
The stall condition, exactly, is going to be the square root of 2W rho CL max S, rho S CL max, right? This is the equation. The idea here is that in your cruise flight, lift is equals to weight, right? That's the idea of the cruise flight. And then we define the, and in your stall condition, you'll get the maximum lift coefficient. We define the force coefficient as this, 1/2 rho V infinity S, right? When you get the CL max, when you have lift equals to weight, this V becomes V stall. And you rewrite this equation, you will get to the stall velocity. Okay, what else? So next one is one from chapter 5. I want you to define the taper ratio and name 4 different types of wings. Let's give it 30 seconds. Okay. Go ahead. Okay, so you have this type of wing. Your taper ratio is going to be this, right? Divided by this, right? CT divided by C R root. Yeah. Okay, what are the name 4 different types of wings? That's the next. That was the next part of the question. Can you name them? You can go. That's all right.
High wing, mid wing, low wing, airflow wing.
That's the location of the wing, though, right? Not the type of the wing. Let's go with Mohammed. We have swept wings, we have tapered wings, we have rectangular wings, and also delta wings. That was the 4 main types you saw in class. Okay, what is the sweep angle? Where is it more important? Where is it more crucial? What type of flight is it more crucial? Go ahead. Exactly. Thank you. So sweep angle is essentially, let's say we have this type of, as Trevor mentioned, will be this angle between, let's call this the y-axis. This angle. We can have sweep angle at the leading edge, sweep angle at the quarter core, and the sweep angle at the trailing edge. And it becomes very important when you're dealing with supersonic flights. Let's try one. Okay. Let's move to the next one. How would aspect ratio affect the stability of the plane? How does it affect the induced drag?
The higher the aspect ratio, the more stable it is.
Mm-hmm.
The less unstable,
Okay.
or the more like
Maneuverable. Exactly. What about the induced drag? How does it change the induced? What was the equation that related induced drag coefficient to the aspect ratio?
It's CO squared over pi.
Okay. So how does aspect ratio affect the induced drag?
Aspect ratio goes down, induced drag.
That's it. Thank you. John. Okay. Next one is how would the angle of twist affect the wing stall? Who knows what the angle of twist was? Let's see if there's any undergraduates. Let's just wait for undergraduates to see. We have a couple of undergraduates here. I mean, most of you are undergraduates. So what was the angle of twist? Go ahead.
It's the difference from the tip of the wing to the center of the wing as it like twists upwards.
Exactly. So essentially, exactly. Thank you. So your wing can be twisted a little bit. The angle of twist is going to be the, let's say this is your airfoil at the root, and this is the airfoil at the tip, right? This angle between these two chords is called the angle of twist. And the question I have is that how would this affect the stall of the aircraft? See, Leighton already has 4 bonus points. 2% of your grades. How would this angle? How do you think this will affect the stall? Any takers? I mean, all 3 of you had your hands up at the same time. Let's go with, I mean, either Jacob or, I mean, all of you have 1 bonus, right? You guys decide who wants to go first. Who is more sure about their answer? Let's go with that person. I mean, you're a 4th person. Don't complicate the problem. Let's start with Paul.
Your angle of attack alpha is changing across your wingspan. So your CL versus alpha graph also changes per your wingspan, which means that the stall location is going to become like, I guess, essentially less depending on the angle throughout the wing. So it'll angle itself like down the wing essentially.
Depending on the angle of twist, if it's positive or negative. Do you guys want to add anything to this? It doesn't change the slope, no. I mean, if you're using different airfoils, yes, it may, but not it won't change just the angle itself won't change the air slope. Okay. Do you want to, Ryan? Huh? Okay. So let's go with Paul. So think about it this way. As Paul said, if you have an angle of twist, let's call this alpha t, angle of twist, alpha twist. and you have an angle of attack. Your angle of attack here is going to be this. Let's call it angle of attack of the tip, right? But the angle of attack at the core, at the root, is going to be alpha twist plus alpha tip, right? Does this make sense? Because it has a different angle, right? So we are going to have a higher angle of attack for this type of twist. We're going to have a higher angle of attack at the root of the wing, which means that your stall condition is going to reach, it will reach an earlier stall you're in because you're already at a higher angle of attack. You'll get to the peak CL sooner when you are at the root, okay? So, next one. That's a grammatical error. It has to be explain the downwash phenomena. How would it change angle of attack, lift, and drag? Hopefully, all of you have an answer for this. We have done this many, many times. Downwash. That's a grammatical error. Yeah. I'm sorry. Yes. That's the downwash phenomenon. Exactly. So you will have pressure or flow leaking from the side, right? Which is not an ideal situation. So what's going to happen to lift, drag, and the angle of attack? It will also reduce the lift, but it will introduce a new drag called the induced drag, right? Okay. Try one. Okay, and the last one. What are the two pillars of the Helmholtz vortex theorem?
The strength of the vortex filament is constant along its length, and the vortex filament can enter the fluid, and this extends the boundaries or form the fluid path.
Okay, exactly. So the two main parts of the Helmholtz theorem, which we use to develop all of these equations we use in chapter 5, was first the strength of a vortex filament is constant. Is constant, and then a vortex filament cannot end in fluid unless it's a like circular shape or it's a closed form and in a fluid. That's why we define these horseshoe vortices, vortex filaments, to help us with the analysis. Okay, so these are all six. These are the max number of conceptual problems I will give you. I can give you more, like we had other concepts that we discussed very briefly. But your like 4 or 5 problems will be all of these. Okay, I may ask you to calculate the stall condition, something like that. Is there any questions about the conceptual parts? Okay, so let's move on to the next parts. The next question, yes. Cannot. I'm sorry.
No, it's okay.
It is. Yeah, I saw the commotion going on at the back. You could have just asked. Cannot end in a fluid unless it forms a curve, which essentially means that when you have a curve, there is no end to it, right? It's a curve, unless it forms a care. Sure. Yes. Not the best handwriting in the world. I know. Constant. Okay. What happened there? Okay, so let's move on to the next part. If you look at your, and if you're watching this online, it is already uploaded. All of these, I forgot to mention this at the beginning of the class. If you're watching this online, we had some comments on YouTube as well that I didn't see, but I don't know who that is. It's just a random username. Yeah, let's move on to the problem 17. It is giving us the NACA 2412 Camber line equation, which can be calculated based on this general equation, right? The general equation you have is y of c is equals to m divided by p squared, 2 multiplied by px minus x squared, and all of those things. But what are m and p? M is the maximum camber divided by 100. So that's for 2412, that's 2 divided by 100, right? This is a discussion we had earlier in chapter 4, I guess, about the numbering schemes, right? What those numbers mean, right? So M in a 4-digit setting will be the first number divided by 100. And P is going to be the second number divided by 10. So for a knockout 2412, your equation of the camber line is going to be equal to, and keep in mind in your book and in your homework, we had z as a function of x. Here it just says y as a function of s. And this is y divided by c. So we are assuming the chord length is just 1 here. I'm going to replace it with z just to make sure we are consistent. So for a 2412, z divided by c is going to be equal to 0.02 divided by 0.4 squared multiplied by 2.4 x minus x squared for x divided by c's between 0, 4, and p, between 0 and p, which is 0.4. And z divided by c is going to be equal to, the next part of it is going to be 0.02 divided by 1 minus 0.4 to the power 2 multiplied by 1 minus 2 multiplied by 0.4 plus 2 multiplied by 0.4 x minus x squared. So in an exam, what I'm going to do is to give you this general equation, give you the NACA number, which is NACA 2412. And the first thing would be I will ask you to find the equation of the camber line, which is this, right? So we are going one step backwards in solving these problems. Okay. So we have the equation of camber line. What is the next step? We are asked to find the zero lift angle of attack. Alpha L equals to 0. How did we find it? What was the equation here? Does anyone remember? What was the equation? You had it in your homework 4. I'm looking for the number. It is problem 3 of the homework 4. What was the equation here? I don't expect you to memorize this, of course, but equation was 1 divided by pi negative integral of 0 to pi dz dx 1 minus cosine of theta d theta. This was the equation, right? But the problem we had was that this dz dx is in terms of x, but the integral is with respect to theta. So what should we do? You have to take the dz dx first. Let me clean this part of the board. You have to take the dz dx first. And then let's say we have taken dz dx. Do we have any trouble in finding dz dx? It's a derivative, right? It's a polynomial derivative, right? And it will be a polynomial derivative on your exam as well. And next step would be to convert this to theta, right? We had an equation for this conversion. I keep forgetting the correct equation, so I have to go back and look myself. It was, yeah, x equals to c divided by 2, 1 minus cosine of theta. So you apply your dz dx. Wherever you have x, you just plug in this equation over there, and you will be getting dz dx as a function of theta. So the next step would be to plug it in here and take the integral. But you have two equations, right? You just have to make sure you convert these boundaries as well, boundaries of the integral, and you have to take two integrals. One integral for this, the first dz dx, second integral for the second one, right? Okay. And for taking these integrals, you usually have to have the integral of cosine of theta d theta. Have a solution. You can have these in your equation sheet. Cosine of cosine squared d theta, cosine squared, cosine cubed, theta d theta. These are provided to you. Yes. You don't have to do it manually, you know. If you have a professional calculator that you can just plug in and get the. You have to expand the integral, though. That's what I want you to do. So I want to make sure that you understand how to expand the integral. And by that, I mean you have to show me that you're taking these two integrals, and these two, integral 2, integral 1, and just write the integral. This is the integral, and just write down the equations you have in your equation sheet for integral of cosine squared, cosine third, and just tell me that I have solved the rest of it with a calculator. Okay? Yes. Do we have a negative sign over there?
Sorry. If we don't have access to like integral calculator for the test, would you want us like to leave it as an integral or just keep solving?
No, you have to solve it. Because the solution to if you have the answers to these integrals, its solution shouldn't take you more than 2 minutes, because you know the answer to the integral, you plug in the values, that's 0, whatever, like pi over 2, right? You know cosine of 0, you just have to add and subtract. It is not a very hard thing to do. You have to, that's why I said you have to expand the integrals, just to make sure there is no discrimination between people who have access to sophisticated calculators and people who don't. Yeah. Any other questions? Okay, so you plug in the values here. You get the alpha and 0 lift angle of attack. Okay. The next step is asking us to find the lift coefficient when it says right here when alpha is 0. So I guess we can find it as well. By 1 to 7, alpha is 5. How can we find that? We are dealing with thin airfoils, right? So you just have to, in your mind, you don't have to do this on your exam. Just in your mind, we have CL alpha. We have calculated for the value of alpha L equals to 0. By definition, CL is 0 over there, right? And we have this lift slope. What is the value of this lift slope for a thin airfoil? 2 pi, exactly. So this 2 pi is going to be equal to CL at alpha equals to 0 minus CL at alpha L equals to 0. This is, we already have the value for it. It is 0. Then you have alpha L equals to 0 minus your target alpha. I'm sorry, you have 0. Your target alpha, which is 0. Let's call this alpha 2, right? So this is alpha 2. Happens to be 0 in this case. Minus alpha equals L equals to 0. You will get the solution. You will find CL. Okay? So what else? We are asked to find CM, moment coefficient at the quarter chord, and also the location of center of pressure. How did we do that? Does anyone remember? We had an equation. It was pi over 4, A2 minus A1. And A2 and A1 was Fourier constants, right? Fourier values. We had this AN is it 1 over 2 pi? I have to go back and double check. Integral of 0 to pi cosine of n theta d theta, which means that your A1, let's just make sure this is the correct equation. Yeah, 2 over pi. There's also dz by dx. Okay, which means that A1 is going to be 2 over pi, 0 to pi, dz dx, cosine of theta, d theta, and A2 is going to be 2 over pi, 0 to pi, dz dx cosine of 2 theta. In an exam, I will probably not give you both of these together. I will either only ask you to calculate the moment coefficient or the 0 lift angle of attack, because it's just continuation of the same things. So it is going to be a little pointless to give you in an exam. And your CM and CM, the quarter chord moment coefficient, is pi over 4 A1 minus A2. We have to move a little faster. What's the rest of it? That's xpc divided by c, the location of center of pressure. We have already calculated whatever we need. We just have to plug in the equation, which is 1 over 4, 1 plus pi over CL, A1 minus A2. Right? Yes. And then, as long as you have found the solution to these integrals, You should be able to find the rest of it. The rest of them just plug and check, right? So the biggest part of these type of problems is to take the integral correctly. And I will either ask you to find the zero leaf angle of attack and CL at a specific point. Just give me 1 second. Or I will ask you to find the moment coefficient at the quarter chord and the location of center of pressure. Yes.
You did say that that was 1 over 4, right?
1 over 4, yes. This is 1 over 4. Okay, let's move on to the next problem. Next problem, I have said to go over the problem 7 and 8 or the last ones. I'm not sure what were the numbers of those. The last problems on your homework 4. Did anyone have any trouble solving those problems? You remember those problems. You have already submitted your homework 4. You are actually already graded on them, on all of them. Did anyone has any problem solving the last problem, last 2 problems on homework 4? What you will probably get is something like the last problem, that's problem 8, right? In your homework 4, which I'm going to give you a transition Reynolds number, right? I'm going to ask you to find the total friction coefficient or total friction drag based on the transition Reynolds number. Do we remember all of those concepts, or do you want me to go over them once more? Is there anyone who doesn't remember these? Okay. Have we seen homework 5? Is there anyone who has already started working on homework 5? I have a couple of people. Is there anyone who hasn't started working on homework 5? 1 person, 2, 3. I guess a lot. Okay. That's all right. So we are gonna go over some parts of homework 5. Let's go over the let's go over the question number 1 first. Question number 1 of the homework 5, which is something you will probably get, is telling us to consider the case where the span-wise circulation distribution for a wing is parabolic. Right? Instead of elliptical, it is parabolic. So gamma is equals to gamma naught 1 minus y squared divided by, here it is telling us it is s, but we could use the book's analogy and do b, right? So if you were confused here, in the book, this is the top view of a wing. We do b over 2, b over 2. Your total span is b, right? Here, in the text of the problem that I have written here, they are going to assume the span is 2s. So don't be confused. And it goes to positive s and negative s. What you're going to see in the homework is this. Right. We are told if the total lift generated by the wing with the parabolic circulation distribution is to be equal to the total lift generated by a wing with an elliptical circulation distribution, what is the relation between gamma naught values for the 2 distribution? So what should we do here? Can you speak up a little bit?
You have to find gamma naught b of the elliptical and compare it to the parabolic by dividing them by each other.
How would you find gamma naught elliptical or parabolic? Not the gamma naught, the circulation, that's the distribution of circulation, right? The only thing we have here is that the lift perimeter span is equals to, let's go to lift. Lift of elliptical is equals to lift of the parabolic, right? How did we calculate lift? It was based on the Kotar-Joukowski theorem. It was rho infinity v infinity integral of circulation, right? Over the wing. So in this case, it can go from negative s to positive s, but we're gonna stay true to the book and go from negative b to b, right? Gamma naught 1 minus y squared 2yb squared dy, right? Equals to lift of the elliptical. What was the lift of elliptical? So this is lift of parabolic. Lift, just to make sure you are not. Who can tell me what the lift of elliptical distribution was?
For elliptical, it's rho infinity
Rho infinity, v infinity,
d pi gamma elliptic
gamma naught, right?
divided by 4.
Divided by 4. So this is something we have already calculated and we have already seen.
And the equation that you calculated is for parabolic, but what you are reading is for elliptic. So you need to change the equation of circulation to change it for elliptic. That equation is for parabolic. Or make the parentheses to the power of half.
Okay, read the question again. Consider the case where the span-wise circulation distribution for a wing is parabolic, okay? If the total lift generated by the wing with the parabolic circulation distribution is to be equal to total lift generated by wing with an elliptic circulation distribution, what is the relationship between the two? So this is the elliptical part, which is to be equal, elliptical, to the parabolic part.
So for solving the equation, you should just consider S equal to B half of B, yeah?
That's it. Yeah. I mean, you don't need to use B. You can just use S here, and B over 2 is going to be S. B over 2 is, I mean, S is going to be equal to B over 2, right? So B is going to be 2S over 4, right? And you will have the equation. And then you can, this is for parabolic. Then you can find the relationship between the two. You just take the integral of 2y squared dy, pretty simple, right? And integral of 1 dy is also simple. You can take those integrals and you should be fine. And you can find the relationship between the two, gamma naught of elliptical and gamma naught of parabolic. Is this clear? Okay. What else? And I mean, for the induced velocity, we also have another equation, but we have already calculated the induced velocity for the elliptical distribution. So you calculate the induced velocity using the integral equation we had. It was the integral of 1 over 4 pi, right? So just make sure 1 over 4, yeah. 1 over 4 pi for the induced velocity. 1 over 4 pi, y naught, 1 over 4 pi, the integral of negative b over 2 d gamma dy divided by y minus y naught, right? The only catch here, it is telling us that we want to find this induced velocity at the symmetry plane, right? Where is that symmetry plane? That's the only thing you need to understand, right? Symmetry plane on a wing, on this type of wing is always at the middle or on the fuselage. So your y naught here is 0. That's it. Just plug in y naught 0, then you should be able to take this integral. You just have to calculate the derivative of gamma with respect to y. Okay. And we have already solved an example like number 2. And the only thing that remains is one thing that I didn't mention. I won't ask you in the exam as well, but it was brought up by a student in my office. I just thought it's not a bad idea to mention this in class today. So problem 3, or the problem 4, the last one, which is numbered 1. That was my error. By this problem 4 is asking you to calculate the induced drag coefficient for a Supermarine Spitfire. And I haven't given you any information about E, the efficiency factor here. Okay? The assumption here, as my assumption, which I shouldn't have assumed this, I should have told you that you already know that Spitfires are very famous British aircraft. You actually dealt with them in your homework 4 as well, and are famous to have elliptical wings. So your efficiency factor here is 1. Okay? You don't need to make any calculation. But if this wasn't a Spitfire, you can actually use the graph that is given to you at the back of the handout, is also posted online. By having the taper ratio and the aspect ratio, you can find the delta. And if you recall, we said delta for most cases, at least for this course. Delta is equals to, we have this relationship for delta, tau, and efficiency factor. So if you know the aspect ratio, if you know the taper ratio, you can find delta, you can plug it in this equation and calculate an efficiency factor. But in an exam, I will give you the efficiency factor. You don't need to make this calculation, and you don't need to have this graph with you, okay? Just in case in your future aerodynamic life, if you became an aerodynamicist, you know this is out there. Is there any questions? Yes.
For question 1, we know that the lifts are equal, and we know that the lifts are proportional to gamma. Couldn't we just compare gamma, because we're given gamma from the textbook under the elliptical chapter? Like, that was my kind of mindset when I went to the chapter.
You are told that lift is the similar, right? Is the same. You're not told the circulation is definitely not the same, right? You can compare the integral of the circulations. That would have been fine. So if you take the integral of circulation over the wing, you would have had the same solution. Yes. Any other questions? Okay. So I guess that's it. Right. See you all on Monday. Good luck with your exam. If you have any questions, don't forget, before leaving, don't forget to write down your names on a sheet of paper. Let's actually do this one. Attendance check. And thank you. And if you end up watching, if you are watching this online, send me an email. If you watch this online later, you can also send me an email. That will actually go towards your attendance as well. And don't forget your project. If you're a graduate student, your project is due in 2 weeks. If you're not a graduate student, you don't have to worry about it.